So, now I will discuss the dynamic behavior of chemical processes. Dynamic behavior of chemical processes. I have mentioned in the last class about this in brief. I mean, what is transient behavior, how we can get the transient behavior. So, we will start from that only. We have a chemical process. This is input, this is output. If we give a change in input variable, we will get some change in output variable, and that is the dynamic behavior, and that we will observe in terms of the change in the output variable. Fine. So, we will consider the different forcing functions. Different forcing functions. First, we will start with step function. First, we will start with step function. So, first I am drawing the step function, how it looks. The function we will represent by f. So, this is f t and this is time t. This is time t. Initially, if the process is at steady state condition, I mean there is no change. Now, we are changing the input variable in this way. So, initially it was 0. Definitely we are considering here f as a deviation variable, that is why that is 0. Fine. F we are considering as a deviation variable. Here f is not function, here f is variable. Note this point. So, since f is the deviation variable, that is why at steady state f equal to 0. Now, we are changing this f value at suppose time t equals to 0, and the magnitude of this change is suppose a. This is the step function which we have represented graphically here. Now, how we can represent it mathematically? F t equals to a, that is the step function. So, if we write the Laplace transform of this function f t, what will be the Laplace transform of this? A by s. So, the Laplace transform of a step function is a by s, where a is the magnitude of that step function. Fine. What is the example of this step function? Suppose we have a steam valve. We have one steam valve. Fine. Now, open the steam valve at t equals to 0. Open the steam valve at t equals to 0 such that Q changes by A units. We have a steam valve. Open the steam valve at time t equals to 0, so that Q changes by A units. Here Q is the steam flow rate, and that is basically F. Fine. This Q is basically f. So, if we change the q by a units at t time equals to 0, that is the example of a step input. So, we can change the load variable, disturbance variable by this fashion to observe the transient behavior of the process. This is the first type of forcing function which is commonly used. Second forcing function is rectangular pulse function. Rectangular pulse function. First we will draw the figure of this rectangular pulse function. Fine. So, this is f t and this is time t. Initially f t is 0. Now, it changes at time t equals to 0 by unit of suppose a, then it remains there up to time b, then it returns to the old value. This is the graphical representation of a rectangular pulse function. Fine. Initially f t is 0, that means the process is at steady state. Then at time t equals to 0, the input function changes by magnitude a, then it remains there for a time duration of b, and finally it returns to the old value. Now, how we can represent it mathematically? F t equals to 0 when time t less than 0, f t equals to a when time is in between 0 and b, fine, and again this is 0 when time is greater than b, fine. So, this is the mathematical representation of this pulse function. This pulse function is basically the combination of two input functions, fine. This is the combination of two input functions. So, what are these two input functions? If we consider one function is f1 and another one is f2, then the graphical representation of f1 is like this. Initially it is at 0 level, this is 0 and this quantity is f. So, f1 t equal to 0 when t is less than 0, and this is equal to a when t is greater than 0, fine. Another function is f2 and this is suppose time t. Initially it is at the value of a, then it is coming back to this value and this time is b. So, f2 t equals to 0 when t is less than b, f2 t equals to a and time is greater than b. Can we write this for the function, second function f2? Can we write this? We are considering this is 0. So, this is a. initial value we are considering 0 and this we are considering a. That means this is f1 t minus b. Here we are considering increasing, I mean it is increasing the step. Here we are considering decreasing. Initial value is 0 and this quantity is a. By that way we can write f2 t equals to f1 t minus b. Fine. Now ft is the combination of these two, f1 t, f2 t minus b. See, minus sign is included here because for f1 function we have considered that the increase of step, but for the case of second function we have considered the decrease of step. That is why negative sign for f2 and positive sign for m2, sorry this is f1. Fine. Now we will take Laplace transform of this, Laplace transform of ft. So Laplace transform of f1 t minus f1 t minus b, this is equal to f1 bar s, and for this we can write e to the power minus bs f1 bar s. So f1 bar s is 1 by as, no, f1 bar is a by s. Fine. That is the step function only with the magnitude of a. So a by s 1 minus e to the power minus bs. This is the Laplace transform of a rectangular pulse function. This is the final form for the pulse function. Now what is the example of the pulse function? If we consider the steam valve, open the steam valve at t equals to 0, show that q changes by a units, hold at the new value for the duration of b, then return to the old value. You just try to remember that configuration, I mean the graphical representation of pulse function. Again I am telling, open the steam valve at time t equals to 0, show that q changes by a units, hold at the new value for the time duration of b and return to the old value. This is the example of a pulse function. Fine. Now we will just modify that figure of pulse function. Previously we have considered the time duration of b, now we will consider the time duration of a. This is ft 0 initially, then this is 0 and this time step is suppose a, and we are considering here 1 by a, this is time t. Fine. So what is the area? Area is 1, a multiplied by 1 by a, that is equals to 1, and this is called unit pulse function. This is called unit pulse function. it is conventionally represented by del A t. Fine. So, this is unit pulse and it is represented by del A t. Now, we wish to consider limit a tends to 0, a multiplied by 1 by a. How much is this one? We are just approaching 0, we are approaching the time 0. So, how much it will be then? 1. How we can represent it graphically? How we can represent this situation graphically? The graphical representation of this is somewhat like this. This is time t equals to 0. This is 0. This function is called unit pulse function, sorry, unit impulse function. This function is called unit impulse function. It is also called Dirac function and it is conventionally represented by del t. This is called Dirac function or unit impulse function and it is represented by del t. So, what is the definition of this unit impulse function? It is defined as equal to 0 for all times except for time t equals to 0. It is defined as equal to 0 for all times except time t equals to 0. So, we can represent this again by minus infinity to infinity del t dt equals to 1. If we consider minus infinity to infinity, then del t equal to 1 within this range, within this time range. Fine. Now, what will be the Laplace transform of this unit impulse function? Laplace transform of this del t equal to Laplace transform of the unit pulse function in addition, I mean if we consider limit a tends to 0, then we can write here unit pulse function. So, this is unit pulse function. Fine. That means integration 0 to infinity limit a tends to 0 del a t e to the power minus s t dt. We are just considering the definition of Laplace transform. Fine. Integration of 0 to infinity limit a tends to 0 and this is the Laplace transform of unit pulse function. We will just take out the limit a tends to 0, integration 0 to infinity del a t e to the power minus s t dt. Fine. This is equal to limit a tends to 0. This part we have already calculated. How much is that? 1 minus e to the power minus SA divided by AS. We have basically consideration in the previous example the time duration B, but in this example we are considering A. So, you just replace B by A, and in the unit pulse, in the discussion of pulse function, we have considered the magnitude, that is A. Here we are considering 1 by A, fine. So, we have derived the Laplace transform of pulse function, that is A by S 1 minus e to the power minus Bs. Just we need to replace B by A and A by 1 by A, then we will get this equation. So, how much it will be? 1. How? By the use of L'Hospital's rule. So, this is the Laplace transform of the unit impulse function. Can you give any example of this unit impulse function? I mean, we can continue the same example. Say we have one steam valve. Can we give the example of this impulse function? It is impossible to realize perfectly, but we can give the example like this: open the steam valve and instantaneously return to the old value. Open the steam valve at t equal to 0, and as soon as physically possible thereafter return to old value. This is the example of impulse function. Another input function is also used in process control, that is ramp function. That is ramp function. We can represent this function in this way: time t, initially it is 0, then it changes like this. Suppose the slope is A, fine. Initially it is 0, and at time t equals to 0 it changes linearly with slope A. So, if ft is the ramp function, then it is 0 when t less than 0, it is at when t greater than 0, fine, and the Laplace transform of this is A by S square. So, what will be the example? Gradually open the steam valve so that Q increases linearly, fine. Gradually increase the steam valve so that Q increases or Q changes linearly, and ramp ends when the valve is fully open. The ramp ends when the valve is fully open. So, these are the forcing functions which are used to observe the transient behavior, definitely in presence of control scheme, but presently we are not discussing the control part, we are just discussing the simulation results, I mean the model output. Next we will discuss the different how to solve the different model structures. Practically most of the chemical processes are nonlinear in nature. Almost all chemical processes show nonlinear dynamics. Fine. Now, analytical solution of nonlinear equations are not available. So, how we can proceed? One option is we can solve the modeling equations numerically. If we have the nonlinear equations, nonlinear model, we can solve it numerically. So, keeping the numerical simulation of the modeling equations, we can proceed for the development of nonlinear model equations. Fine. Another option is we can linearize the nonlinear model. Fine. So, we can linearize the nonlinear model. So, linearization of nonlinear equations or nonlinear model, and we can go for analytical solution. If we can linearize the nonlinear equations, we can go for analytical solution. Third option is we can develop the linear model for the nonlinear processes, and we can solve the linear equations again analytically. So, there are three options. One is development of nonlinear model and go for solution by the use of numerical techniques. Another one is linearize the nonlinear equations and follow the analytical solutions, and third one is develop the linear model structure and simulate analytically. But this third option was used in the past. Nowadays it is not used due to the advancement of different mathematical techniques. So, this option is quite old, so we will not discuss any more this. Fine. In the first option, we have option to model the process by the development of nonlinear equations and the solution of those equations numerically. I hope you have started the numerical simulations in your mathematics courses. So, we will not discuss about that in more details. I mean, we do not want to discuss in this course the numerical simulation of nonlinear equations. Second option is linearization of nonlinear model structure. So, that we will discuss in brief. Fine. So, first we will start the linearization of single variable system. Linearization of single variable system. We will consider a simple ordinary differential equation represented by dx dt equal to function of x and t. Suppose this is equation number 1. Here x is the only variable, I mean dependent variable, and t is the independent variable. That means x is also varies with time. So, we can omit that time t within this function. We can write in this form also. This is suppose equation number 2. Now, we will linearize this function f according to Taylor series expansion. So, we will use the Taylor series to linearize f x. Accordingly, if f x equal to f x naught. Here x naught is the reference x, I mean reference value of x, plus df dx at x equals to x naught, x minus x naught, plus d2f dx square at x equals to x naught, x minus x naught whole square divided by factorial 2. dnf dxn x equals to x naught, x minus x naught to the power n by factorial n, like this. This is the Taylor series expansion of f x. Neglecting the term of order 2 and higher, neglecting the terms of order 2 and higher, we get f x is approximately equal to f x naught plus df dx at x equals to x naught multiplied by x naught. You give this Taylor series equation as equation number 3. The Taylor series expansion of f s, you put equation 3 for that, and this approximate linearization we are representing by equation 4. Now, this linear approximation is satisfactory when x is very close to x naught. This linear approximation is satisfactory when x is very close to x naught. This is f x, this is x. Suppose this is the function f x. This point is x naught and corresponding f x is f x naught. Now, if we linearize with respect to this point, so this is basically this linear function is represented by plus df dx at x naught, x minus x naught. So, from this graphical representation, it is very clear that the linear approximation is satisfactory when this x is very close to x naught. If we move away from this x naught, this part is not linear at all, fine. So, the deviation increases as we move far from x equals to x naught. Now, we can write equation 4 like this way also, dx dt equals to f x naught plus df dx at x equals to x naught, x minus x naught, because f x equals to dx dt, that is our equation number 2. We have just replaced f x equals to dx dt in equation 4, and then we get equation 5. This is a linearization of f x according to Taylor series expansion. Now, we will take one example to linearize the model of that particular example. So, we will consider the example of a liquid tank system. Fine. This is the schematic of the liquid tank system. Liquid height and cross sectional area of the tank. Input flow rate is Fi and outlet flow rate is F0. We have derived earlier the modeling equation for this system. The modeling equation is A dH dt equal to Fi minus F0. This equation we can derive based on total mass balance. Fine. Now, this outlet flow rate is basically the function of liquid height. The outlet flow rate F0 depends on the liquid height in the tank. We will consider two cases. In first case, we will consider F0 is proportional to H. Anyway, you give this as equation number 6. In the first case, we will consider F0 is proportional to H. That means F0 equals to beta H. If we substitute this in equation 6, I mean if we substitute F0 equals to beta H in equation 6, then we get A dH dt plus beta H equal to Fi. Fine. If we substitute F0 equals to beta H in equation 6, we get this form, and this is a linear ordinary differential equation. This is a linear ordinary differential equation. So, there is no need of any linearization. Fine, we can solve it analytically. In another case, we will consider this F0 is proportional to root H. F0 is the square root of liquid height in the tank. That means F0 equals to say alpha root H. Now, if we substitute again F0 equals to alpha root H in equation 6, we have A dH dt plus alpha root H equal to Fi. If we substitute F0 equals to alpha root H in equation 6, we get equation 7. This is not a linear ordinary differential equation. So, which nonlinear term is present in this equation? The nonlinear term is alpha root H. So, we will linearize this alpha root H term using the Taylor series expansion. Fine. We will linearize this alpha root H term using the Taylor series expansion, and then we substitute that in equation 7. So, according to Taylor series, alpha root H equal to alpha root H naught plus differentiation of alpha root H at point H naught. Here H naught is the reference height. h minus h naught. Similarly, if the second term, the second derivative will be like this at h equals to h naught, h minus h naught whole square divided by factorial 2, fine. We will neglect the terms of order 2 and higher. Neglecting terms of order 2 and higher, we get alpha root h equals to alpha root h naught plus alpha divided by 2 root h naught multiplied by h minus h naught, h minus h naught. This is the final form of alpha root h after linearization. Now, we will substitute this alpha root h term in equation 7, substitute it. If we substitute in equation 7, then we get f dh dt plus alpha divided by 2 root h naught multiplied by h equal to f I minus alpha by 2 root over of h naught. This is suppose equation number 8. So, this is the linearized form of the nonlinear model or nonlinear modeling equation. Now, if we substitute h equals to h naught, if we substitute h equals to h naught, equations 7 and 8 they are identical, you see. If we substitute h equals to h naught, equation 7 and equation 8 they are same. Equation 7 represents the nonlinear form and equation 8 represents the linear form. Exactly at h naught they are identical, fine. So, that is why we have mentioned earlier that the linear approximation is satisfactory when x is very close to x naught. So, this is the linearization. Now, we will try to represent the model in terms of deviation variables. We will represent this model in terms of deviation variables. How we can do that? At steady state, x is basically represented by xs, fine. X at steady state we will represent by xs. If x equals to xs at steady state, then we can write dxs dt equal to 0 equal to function of xs. See, the steady state value of x is xs, xs is basically constant, that is why the derivative of that constant term is 0, fine. And this is the function of x. Now, we are replacing x by xs, that is why that is f xs. This is say equation number 9. Now, according to Taylor series expansion, we can write f x just by replacing x naught by x s, dx dt equals to f x s plus df dx at x equals to x s, x minus x s. The linearization of f x we got earlier. Here we have just substituted x naught equals to x s and we get equation 10. Now, we will just subtract, we will subtract equation 9 from equation 10, subtract equation 9 from equation 10. Then we can write differentiation of x minus x s dt equal to df dx at x equals to x s multiplied by x minus x s. This is equation number 11. In the next, we will consider one deviation variable, that is represented by x prime equal to x minus x s. X naught is the deviation variable and that is equal to x minus x s. Then equation 11 becomes dx prime dt equal to df dx at x equals to x s x dot. Simply we have substituted in place of x minus x prime, sorry, we have substituted in place of x minus x s x prime. Then we get equation 12. Now, we will continue that example again, that liquid tank system. So, previously we got the linearized form for the liquid tank system, we got the linearized form in equation 8. So, the linearized form is a dh dt plus alpha divided by 2 root h s multiplied by h equals to f I minus alpha by 2 root over of h s. Say this is equation number 13. We get equation 13 from equation 8 directly, fine. So, for the liquid tank system, this is the linearized form. At steady state, this equation 13 yields f dhs dt plus alpha root h s equal to f I s. To represent the steady state, we have included suffix s with all variables, fine. Then we get a dhs dt plus alpha root h s equals to f I s. Now, we will just subtract equation 14 from equation 13. If we subtract equation 14 from 13, we get a differentiation of h minus hs plus alpha divided by 2 root hs h minus hs equals to fi minus fis. Now, we will define two deviation variables. One is fi prime, that is fi minus fis. Another deviation variable we will define, that is h prime equal to h minus hs. These are the two deviation variables. Now, if we write the above equation in terms of deviation variables, we finally get f dh prime dt plus alpha divided by 2 root hs h prime equals to fi prime. This is suppose equation number 15. So, for the liquid tank system, after linearization we got one equation, and in terms of deviation variables we got equation 15. Fine. So, this is basically the linearization of nonlinear equations for a single variable system. I mean, only one nonlinear equation is involved in this example. Fine. In the next class, we will discuss the linearization of multivariable systems. Thank you.